For centuries, humans have looked up at the night sky and wondered about the nature of the cosmos. What is space? What is time? Are they fixed backgrounds upon which the universe plays out, or something more dynamic, more mysterious? In the early 20th century, Albert Einstein shattered our classical view of space and time as separate entities. His theory of relativity proposed that space and time are interwoven into a single continuum, and that this fabric is shaped by the presence of matter and energy. This new vision of the universe doesn't just change how we measure motion or predict celestial mechanics. It changes how we understand the fundamental structure of reality itself. In this extended exploration, we will journey from ancient conceptions of time to quantum speculations about the nature of reality. We'll explore how Einstein revolutionized our view of the cosmos, what black holes and wormholes reveal about the edges of physics, and how future theories may redefine the very meaning of space and time. Before the 20th century, the dominant model of physics was based on the ideas of Sir Isaac Newton. According to Newton, space was a fixed, unchanging stage upon which matter moved, and time ticked forward at a constant, absolute rate. His laws of motion and universal gravitation could predict planetary orbits and falling apples with extraordinary precision. But there were cracks in the foundation. In the 19th century, James Clerk Maxwell formulated a set of equations that described electricity and magnetism as a unified force, electromagnetism. These equations predicted that light was a wave traveling at a constant speed. However, this clashed with Newtonian mechanics, which assumed that speeds should be additive. If you shine a light while moving, why doesn't its speed appear to change? Einstein's answer came in 1905 with his special theory of relativity. He proposed that the laws of physics and the speed of light are the same in all inertial frames of reference. This meant that space and time had to adjust to keep the speed of light constant. Time could dilate and lengths could contract. The faster you move, the slower time passes for you, and the shorter your measuring stick becomes. But the real revolution came in 1915 with general relativity. Here, Einstein proposed that mass and energy curve space-time, and that this curvature tells objects how to move. Gravity was no longer a force, but the result of bent geometry. Earth orbits the Sun not because it is pulled by an invisible hand, but because it is following a curved path in space-time. This idea was tested during a solar eclipse in 1919 when starlight was observed bending around the Sun, just as Einstein predicted. Overnight, he became a scientific celebrity, and the universe became a far stranger place. Einstein's field equations describe how matter and energy influence the curvature of space-time. At the heart of this idea is the metric tensor, a mathematical object that describes the distances and angles in a given space-time. The shape of space-time determines the behavior of particles and light. A planet moving around a star follows a geodesic, the closest thing to a straight line in curved space. Light bends not because it's pulled by gravity, but because it travels along the shortest path in a warped geometry. The strength of the gravitational effect depends on the curvature. Near Earth, the effect is weak, but near a neutron star or black hole, space-time is dramatically distorted. These ideas are best visualized with analogies, like a heavy ball on a rubber sheet. But real space-time is four-dimensional, and its curvature isn't into another dimension, but inherent in the relationships between space and time. Gravitational waves, ripples in space-time, were predicted by Einstein, but only directly detected in 2015 by LIGO. These waves are generated by accelerating masses, such as colliding black holes or neutron stars, and stretch and squeeze spacetime as they pass. Their detection not only confirmed a major prediction of general relativity, but opened a new window into the cosmos. Black holes are perhaps the most extreme expressions of Einstein's theory of general relativity. They are regions of space-time where gravity is so intense that nothing, not even light, can escape. This occurs when a massive object collapses under its own gravity, compressing all its mass into a point of infinite density known as a singularity. The boundary surrounding a black hole is called the event horizon. Once an object crosses this threshold, it is lost to the universe forever. The event horizon is not a physical surface, but a point of no return in space-time, where all paths lead inward. Einstein's equations predict singularities, but they also signal a breakdown in the laws of physics. At the center of a black hole, space-time curvature becomes infinite, and our current theories can no longer describe what happens. Black holes come in different varieties. Stellar mass black holes, formed by collapsing stars. Supermassive black holes, found at the centers of galaxies. Primordial black holes, hypothetical remnants from the early universe. Despite their ominous reputation, black holes are not cosmic vacuum cleaners. You could orbit a black hole safely, just as you would a planet, as long as you stay outside the event horizon. In 2019, the Event Horizon Telescope collaboration released the first image of a black hole's shadow in galaxy M87. It was a stunning confirmation of general relativity and the geometric nature of gravity. Time travel is a tantalizing concept made popular by science fiction. But is it possible according to physics? Einstein's equations allow for solutions known as closed timelike curves, CTCs. These are loops in space-time that could, theoretically, allow an object to return to its own past. One such solution is the Gödel metric, which describes a rotating universe. Another possibility is the Tipler cylinder, a massive, infinitely long spinning cylinder that could twist space-time around it. Then there are wormholes, or Einstein-Rosen bridges, hypothetical tunnels connecting two distant regions of space-time. If one mouth of a wormhole were moved relativistically, time dilation could make one end younger than the other, creating a potential time machine. But time travel introduces paradoxes. The grandfather paradox. What happens if you travel back in time and prevent your own existence? The bootstrap paradox. How can information or objects emerge from a loop with no origin? To date, there is no experimental evidence for time travel. Many physicists believe that quantum effects or unknown laws may prevent CTCs from forming, a principle called chronology protection, proposed by Stephen Hawking. Still, the theoretical possibilities remain fascinating. They push the boundaries of what we understand about causality and the structure of the universe. When we talk about space-time, we must also discuss the large-scale structure of the universe. Observations show that space itself is expanding. Galaxies are moving away from each other, and the farther they are, the faster they recede. This led to the discovery of the Big Bang, a singular point in the past where the universe began expanding. This expansion gives rise to a cosmological horizon, a limit beyond which we cannot see, because light from those regions has not had time to reach us since the beginning of the universe. This horizon defines our observable universe. Einstein originally introduced a term called the cosmological constant, lambda, to counteract gravity and keep the universe static. He later called it his greatest blunder, but the concept was revived in the 1990s when astronomers discovered that the universe's expansion is accelerating, driven by a mysterious energy permeating space, dark energy. Our universe may be flat, open, or closed, depending on the total density of matter and energy. Current measurements suggest it is very close to flat, with dark energy making up about 68% of the total energy content. The fabric of space-time is not static, it is stretching. And this stretching affects how we perceive time, light, and even the fate of the cosmos. Despite its elegance, general relativity is not the final word on gravity. It does not work well with quantum mechanics, the theory governing particles and forces at the smallest scales. Unifying the two into a coherent framework, quantum gravity, is one of the greatest challenges in modern physics. Several approaches seek to bridge this gap. String theory proposes that all particles are tiny, vibrating strings. Gravity emerges from one type of vibration, and the theory requires extra spatial dimensions. Loop quantum gravity suggests that space is made of discrete loops woven into a fine fabric, and time emerges from their evolution. Causal dynamical triangulations build space-time from simple building blocks, like triangles, in a quantum way. Other bold ideas include emergent space-time. Perhaps space and time are not fundamental, but arise from more basic quantum processes. Holographic principle suggests our 3D universe could be described by information encoded on a 2D boundary. These are not just mathematical curiosities. They have implications for understanding black hole entropy and the information paradox, exploring multiverse scenarios and the landscape of possible universes, clarifying the nature of time itself, why it flows in one direction, and whether that flow is fundamental or emergent. The search for a theory of everything continues. Each discovery peels back another layer of the cosmic onion, revealing a deeper, more unified reality. Einstein's insight that space and time are part of a dynamic, interconnected fabric has transformed our understanding of the universe. Space-time bends under mass, flows with energy, and carries the echoes of cosmic events. It holds within it the birth of galaxies, the death of stars, and the whisper of gravitational waves. We now see space and time not as a stage, but as active participants in the cosmic drama. They tell matter how to move, and matter tells them how to bend. From the smallest particles to the grandest galaxies, all things are embedded in this fabric. And we too are part of it, woven from stardust, dancing on threads of gravity, journeying through a universe that is still expanding, still evolving, still mysterious. The story of space and time is far from over. With each new discovery, we weave a richer, more intricate tapestry, one that may someday reveal the full pattern of existence.